Hey everyone, I'm Carlos and welcome to a new book discussion of productbookclub.com. Every month we discuss online a book about product management together with the author and other product colleagues. If you want to find the recordings from our previous discussions and also join us and participate on the upcoming ones, go to productbookclub.com. To find out how to support the book club and help us keep it running without any ads, check the links in the description. Welcome everyone for joining the Product Book Club. We join once a month to discuss a book related to product management. And today we're going to discuss Data Science for Business by Foster Provost and Tom Fawcett. And we have Foster on the call. Very excited to have him joining us. Again, for the new ones, please feel free anytime, you can make questions, discussions, right? I think Foster, you're very curious to hear ideas maybe for the second edition of the book, right? So let's make it a nice discussion. And maybe Foster, we're going to start with an introduction about yourself.
Yeah, sure. I mean, it's kind of funny. I was thinking about this, what I was thinking about, obviously, sort of doing this, and I'm thinking about, I kind of have been secretly a product guy for my whole career, even before I was in data science. I'm kind of old, so I'm back in the mid '80s. I actually worked for U.S. Steel, and my title was systems analyst. But what I ended up doing was going out and finding, like, these were internal customers that we were working with, going out, talking to the customers, figuring out what problems they had and what they really needed for solutions, and then going back and then solving it. But I didn't like the solving it part. I mean, I didn't like the actual physical, like, coding up the solutions part nearly as much as I actually liked going out and figuring out the problems to solve. And then like, oh, here are the 12 problems you better not solve because we've had workarounds for 10 years. And if you fix those, you actually do more damage, And so that always was kind of a fascinating thing to me. And then I started my career as a data scientist in the early '90s, and I went to I consulted for a little while, and then I went to the phone company, what's now Verizon. It was 9X at the time, and and it turned out my job was like find cool things to do with machine learning and then do them, right? And so again, I was like a kind of a product. I mean, I had to then do them too. So I have this sort of science side of things, but an awful lot of me ended up being like product, and we had some great. Mostly, I worked mostly with operations there, so it was internal product, fraud detection, and we did customer contact management, but it was really managing how you would contact the customers. And then kind of fast forward, I mean, then I have like a professorship thing too, which is another. I guess even in the professorship, what I do is I design new classes a lot, and so I'm really like actually a product guy, even as a professor. And then I started up a bunch of companies. And there, once again, it was like, let's figure out what actually we can do that actually would be the basis of like a new company. One of the companies is Integral Ad Science, which IPO'd this year, by the way.
Nice.
And now I'm working full time for Compass, and I'm my official role is heading up AI strategy. But it's really, once again, figuring out what are we going to do with machine learning, and then sort of figuring out how to get it done. And so I'm kind of a product guy. And the book, kind of, I think, you picked, for your product book club, you picked a data science book. And so I think you must have kind of realized that I'm secretly a product guy.
Yeah, I did that. I think what I mentioned on the emails, we discussed a bit, right? I think what I found, I mean, personally, I'm more like from the product role. One of the main takeaways was indeed the expected value framework, right? Which sort of like changed a lot the way how I would approach it, and of course evaluate the solution, right? And I know you also wanted to talk a bit about that, and I think you also mentioned you had another framework in the works.
So which I hope will go into the second edition. So let's talk a little about the expected value. And I don't know how many people read through the whole thing, so let me just give a little bit of background. But please ask questions. It's okay if you didn't read the book; you can still ask me. I'm not gonna, it's not like you're my student, and I'm gonna say you should have read the book, right? So one of the hard things in actually building products with predictive analytics is really what a lot of the book is about. There's other things in there that's not predictive analytics, but predictive analytics is really the area of data science that has had the most impact for years, right? And so when you're applying predictive analytics, I think one of the biggest challenges and one of the biggest places where you see failures, especially when the scientists and the engineers are kind of like somehow or other in charge of making product, right? Is that basically they just are kind of well, we built some machine learning models and therefore they're good. We did some standard machine learning evaluations, the kind of things you would see in a research paper, partial. I mean, I'm not really blaming them because that's all they learn in their machine learning classes, right? And therefore it's good because our classes taught us that this was what it meant for it to be good machine learning, right? It doesn't mean it's going to ever, first of all, solve anyone's problem, but even forgetting about customer stuff and things like that, it's not clear it's going to solve the business's problem, right? And so the way a framework that actually ends up, I think in the book, I have 3 different ways in which you can use the expected value framework to help you, which we can talk about. And again, I'll have a 4th way that it's kind of a little twist on it that I'll bring up in a second, right? But it's basically like, okay, a lot of what we're doing when we're applying predictive analytics is really essentially comes down to figuring out how can we improve value. One of the problems is a lot of this stuff is probabilistic, and so on, right? And so you can't just say, okay, it's going to have such and such a value, right? And so you could say, if it were to be this, right? And so here is where the expected value comes in. You could say, if this were to happen, I could say what the benefit would be. If this other thing were to happen, we're going to incur a cost, right? If this thing were to happen, right? And so now you're starting to think, wait a minute, what if I could put probabilities on those different things of happening, right? Then I could actually apply a standard, very simple. I mean, the framework's so simple. It's like, why doesn't everybody use this? Yeah, but okay, right? And so the idea is if I could put probabilities on these things, right, then I could actually compute some idea that in expectation, this one would be better than that one or something like that, right? And well, guess what predictive analytics does? It gives you probabilities, right? And so, right, it's like so natural to think about this. And again, we can get into some details. I don't want to just be a monologue here. So that's kind of the idea. And so you can use this when you're deciding, for instance, how to put together the decision logic for the product. Which, by the way, again, we could talk more about that if you want to. That's somewhere where basically it's like gets lost. Because product people very often just don't have the conceptual toolkit to be able to think through that. And the machine learning people don't, and we're never taught that. But you have to think, what would be the decision logic? Actually, expected value framework helps you there. Which is the better machine learning algorithm, right? Expected value helps you there, right? How do I actually take a problem and decompose it such that I can even apply machine learning? So you remember, I don't know if you got toward the end of the book, there's a whole chapter on actually using this for what I call analytic engineering. Expected value helps you that. Why? Because it decomposes things into values and into probabilities, sometimes a bunch of them. But once you decompose them, you can ask, can I use a machine learning model for this? Can I use do I need a machine learning model, and so on. So I'll stop there. But again, and let me get back to the other thing later, because we have at least one hand up now and maybe some questions.
Yeah, it's Cindy.
Yeah, I was wondering if you would use the expected value framework also for prioritization on which models to even develop. So if you say, right, in the book, you had an example of the marketing improvement, right? If we were to target, and this is the cost, but that kind of assumes that you already have the model. Would you, and building a model takes time. Mm-hmm. Would you recommend using this framework even before building a model? Right. So
the answer is yes, but let me kind of break down the question because there's several things that you might mean there. One is like problem selection in the first place. Like, what problem are we even working on? And then once the problem is selected, there's still a lot of questions about what kind of models might you use? What kind of machine learning algorithms would you use, right? My feeling is, yes, one ought to use, if one is trying to solve business problems, one ought to use expected values for all of those. The answers are a little bit different. You nodded when I said, even think about what problem to work on. And so that actually leads to the other kind of new framework. It's really taking the expected value framework and kind of thinking about it in this even grander, with this even grander problem of like, what should we even do, right? So, so let me talk about that. So what I see is one of the, probably the #1 challenge to getting things done with machine learning in organizations is the inability to basically say what's going to be the ROI if you haven't done it yet, right? This is like the fundamental challenge. Either you have somebody, a leader, somebody at like the C-level leadership who understands like machine learning and is, or came from research and development, right? In both cases, the idea is, of course, you don't know before you try it. But other than that, everyone's so used to basically like, oh, that's a good idea. Make a business case, show me what the ROI is going to be, and then I'll prioritize it in my process that's going to take into account other projects that, that I might work on. And then the frank, honest, like machine learning people would be like, you can't do that. Right? I mean, you can make stuff up, but we can't do that. How do we know? I mean, how do we know what the ROI is? We don't even know if the models are going to be able to capture anything in the data. Right? We don't know how well we'll be able to predict these things. You would have to be able to predict these things, right? And so, what I found actually really works is, it's kind of like what I did for a long time is make arguments that this is like R&D and all this kind of stuff. And yeah, they kind of got it, but it wasn't in like decision makers' frameworks. Like you have some stakeholder, it's not in their framework for how they do business. As soon as you say R&D, it's like a dirty word to a lot of like C-level people. They had bad experiences with R&D. I don't want to waste, my time with a bunch of academics, in their ivory tower coming up with stuff that is not, that's not going to give me any value, right? So, what I sort of pivoted and I like, look, their language is something. They don't always use ROI, but it's something that is essentially ROI. Let's just move this into the language of ROI. We need to add one thing, and that is expected ROI, right? And so we basically talk about expected ROI. And so then we can say, if we can break down the prioritization, and I do this, by the way, all the time now. We can break down the prioritization. There's 3 components, right? There's the I, right? Okay, yeah, talk to the engineering managers. That's not really a big deal. I mean, they're already estimating this. If you don't have any machine learning people, the I might be infinite. But so if I'm going to forget about the I, right? Then there's the R. But now you've changed the value, the question of what will the value be. You ask the question, what would be the value if successful, right? If we actually could do the machine learning, right? If we could get a certain level of accuracy, it can be conditional. It could be saying like, if we get such and such a level of accuracy, whatever measure of accuracy is the appropriate one for the particular problem, right? If we could get this level of accuracy, then we would have this level of value. That kind of thing we could do. That's just basically coming through, working through a standard, like what would be the value of doing this kind of an exercise. Right. And by the way, and then the other things in the book about applying expected value, you dig down in there, and then you could actually apply some of those other, sort of lower level expected value calculations. Right. And then the last piece, which was the one that the reason we couldn't answer it before, is the piece about like, yeah, okay, well, what's the likelihood that we're going to succeed here? Right. Right. And so, but you've separated these out. Right. And so I found that if basically you could basically say high, low, medium, you don't have to actually, in fact, you're never really calculating the expected ROI, right? You're basically putting together something that you can use to rank the projects and to make an argument like this would have a lot of value if we would succeed. It has medium likelihood of success. This one has a very small likelihood of being of value if we were to see a very high likelihood of success. Okay, decision maker, would you rather invest in something that has a higher chance of failure but would be a really big win, or would you rather invest in something that we're pretty sure we can do and it will give a marginal improvement, right? and they'll be like, oh, can you give me some numbers on that? We can make up numbers for the success and show you what the difference, for the probability of success, show you what the difference would be. We could do, this is probably kind of an obvious thing. You could do a sensitivity analysis. Like what if it's, were to be, what if the probability were to be, such and such or such and such. I've never needed to get into those details. Really, people, the stakeholders understand, like, yeah, okay, you can't estimate that, but you're telling me now, you feel like, it's not really feel like. I can, and again, once you understand the fundamentals of the machine learning, I'll give you a concrete example in a minute. You can estimate the likelihood, the likelihood of the project succeeding, right? It's basically like, all right, I go down, I lay it out as a machine learning problem, and then I say, do I have all the pieces I would need, right? Have I known these kind of problems before, and they generally are solvable? Is it a brand new thing that, as far as I know, nobody has ever done? All right, it's going to have a much lower, I'm going to have a much lower confidence in the likelihood of success. And then I think some of it is just fundamentally, some problems are just fundamentally harder. So I can give you a concrete example. So right now I'm working for Compass, the real estate tech giant. When I went there were, we identified, like, the first thing I did was just go through and learn everything I could about real estate, talk to all the customers, talk to all the people internally. There are a lot of product people who had lots of ideas for, like, how AI might help. And I had scores of different ideas, right? And so I just went through and I started to do this kind of a rough, expected value, really just laying out these 3 different components, and so let's take 2 different ideas. One was, what if we were to take these actions? Could we reduce the time that an agent's homes spend on the market? That would be a big value. Our customers are the agents. If their homes spend less time on the market, they really like to have their homes spend significantly less time on the market, right? And so let's say that there are some actions that people are proposing to do that. So that'd be one, project 1. Project 2. We want to get them new business. So we want to basically say, if we'll recommend that you go out and you go talk to this homeowner. You talk to this homeowner, you're going to be the most likely to get new business. And so now we're going to basically say, we're going to help you to optimize your efforts. Okay, so that's project 2. We call those business growth recommendations. Let's think about the EROI of both of these. And so let's think about the first one. And we'll forget about the I again. That's for the engineers to worry about, right? The value. You reduce the time on market. What are the value? What are the dimensions of value? Well, we already said, we know we're going to make them happy. Yeah. And then my response would be, and so what? Yeah. And so what? We make our customers happy. Yeah, all else being equal, we'd like to make our customers happier, right? But all else isn't equal, right? So what? Does this actually give them some financial advantage? It does give them a little financial advantage, mostly because they invest things, like they put money in. They put their own money in sometimes to help the homeowner to stage the home or to fix the home up, because the homeowner doesn't have $10,000 to fix the home up, but the agent's like, come on, you need to do some landscaping out front, and you need to get a new countertops in the kitchen. Otherwise, everyone's going to turn around before they even walk. They walk in the door and they're going to turn around because it's going to give them a bad experience. And the homeowner might say, but I am not spending $10,000 before I sell my house, right? And so the agent might actually front that. So there are costs that now the agent has that on the hook until the home gets sold, right? And then they have to spend their time. So the longer it's on the market, they're always spending their time when the home is on the market trying to get customers. So you could probably quantify that. Okay. But I would probably say that is small to moderate value.
But is there a limit how many homes one real estate agent can handle? So if say they could only handle 3 at a time, the faster they move, the faster overall business goes, right?
Yes, that is true. That because of there's no technical limit. It's really just fun because of their resource constraints. They maybe can't. I think that was what you were implying. And so yes, so they could handle more business, but my understanding of the agents is that's not the constraint, right? It's not like, you know, you take the home and it spends 3 weeks on the market and you take it down to 1 week, right? It's not like they do 52 homes a year. No, they do like 10 homes a year, right? You know, so or 10 to 20 maybe homes a year. So it's not like, oh my God, I'm turning down business because I just have these homes on the market. I think you're correct, but I think it's just not the supply. Well, the demand isn't there to need to require them to increase their supply capacity. All right, what about, so moderate value, maybe low to moderate value if successful. What about the likelihood of success? It turns out it's a super, super duper hard data science problem, right? Because why? Because you're estimating whatever the action is, right? You're estimating the causal effect of that action, right? Estimating causal effects is really, really hard. We can do it. It's just one of the harder problems. And so can we do it? Do we have the right data to do it, right? That means you have to have data on people taking the actions. If it's a new action that you're putting out there, you don't have any data. So when people are saying is, oh, we want to build a system, use machine learning to recommend the best action. You think, have you ever actually given that action out before? If you haven't, like, you know, you're not going to be able to use machine learning to predict the next action, the best action. You're going to first have to go out there and start giving the action out. And probably you want to do some kind of an A/B setup because you also, once you start giving the action, right, you don't have any data on not giving the action unless you were careful, right? You know, and so on. You never observe for any given home what would happen in both conditions. Right? You only observe, you know, what would happen, in a single condition, right? This is the sort of dirty secret of A/B testing, right? Is you never observe the actual effect of the A or the B on anybody, right? You just observe what happens if you give them, and then you're like, and then statistics, you know, and now I can draw a conclusion, right? You know, okay, now we go back over to likely to sell. If you can actually start telling them which homes they're most likely to win, and you can be accurate, most likely to win. Yeah, that includes like whether they're going to sell, whether it's going to be a good property for this agent or whatever, and they're going to be most likely to win them, and you can significantly improve their win rate, right? Now you're basically changing the number of homes, right? And, you know, our agents on average make about $25,000 for a home, right? And so, you know, you give them one more, they just made 25,000 more. So all you got to do is over the course of a year, one of those actions had to lead them to get one more home than they otherwise wouldn't have. So this could be a big time. The value, if successful, could be really big. And then what about probability of success? It turns out, like, if you take we're doing this, by the way, we estimate the likelihood to sell. Yeah, you know, I mean, I've been involved in marketing and sales and so on. You can estimate that some things are more likely to sell than others, right? We probably can do that. Furthermore, it's a rather straightforward machine learning problem. It's not a causal problem. We're not saying you're going to go out and talk the person into selling their house. No, you just want to go out and talk them into, if they're going to sell their house, you should work with me, you know. I'm the best agent. You should work with me, right? And so this is like the application. And so the idea would be that the expected ROI is much higher for likely to sell than it was for the other projects. So that would be an example of that's actually a real example. We did exactly that, you know, along with a whole line of other products. And it turned out that I picked likely to sell because that's the product that ended up at the top. You know, I kind of summarized it really quickly. It wasn't quite so straightforward when we actually did it.
Because I think basically what you're trying to say is that also with the expected ROI, right? I think a main differentiation you do at the beginning is also split sort of like the impact if you were to get it right, and then also the uncertainty separately.
Yes,
right?
exactly. And that's kind of the key thing. And that's, you know, that's what kind of allows you then to proceed, I think.
Yeah.
Because otherwise it's basically like, well, we don't know if we can even do this. Right. And it kind of stops you, you know.
Yeah. Nice. I wanted to see if maybe someone from the call has a question or comments, something.
I would have one if nobody else has one. You shortly mentioned in your description now the where experimentation fits in. So if you want to do machine learning, you probably need the data, and that is where experiments comes in. And I'm working in the tech industry, and I've grown up in the tech industry. So I never even have worked in a company that had a real life product, as in like something that I can touch. So I'm like, my reality is that we do experimentation for everything, because usually it doesn't break anything. And you know, when it comes to experimentation with humans, with customer service agents, so that then we're very, very careful. So there we're kind of like, yeah, maybe let's not do that. Yeah. But everything that's software, it's kind of like, yeah, sure, let's just try it out, because there's nearly no cost to that. How would you see that in other parts of the business?
Yes.
Yeah.
So let me first address. Oh, go ahead.
No, I just wanted to add, indeed, because I had a similar question on like, yeah, how would you maybe like do the trade-off, right? Of I've seen indeed, I think maybe a bit more like opposite to what Cindy is mentioning now, that sometimes I think machine learning has got more like popularity, right? So if there's a company that wants to invest a bit more on a new technology, then maybe they would invest in building machine learning when maybe they don't have a proper way of testing it, right? So yeah, I don't know, how would you also see that trade-off, right? I know in the book you mentioned that that's a whole different landscape.
Yeah, let me talk about the A/B testing first, and maybe this will come through, and then otherwise, and if not, ask me again when I'm done. So the yeah, A/B testing is really interesting. I agree, and let me make a caveat on tech companies. B2C tech companies, right, pretty much have A/B testing kind of in their DNA, you know, or should, right? And again, there are cases where it might be unethical to do an A/B test or something like this. These are really exceptions, you know, and yeah, and as Cindy mentioned, companies are careful, right? Even with tech companies, with B2B, it's actually much harder, right? You know, you're doing something and then you're telling one of your business customers, yeah, sorry, we just randomly didn't give it to you, right? You know, that's potentially really problematic. And so B2B companies, I think it is harder. And like for us, we're Compass, for us in my Compass, with my Compass hat on, we're a B2B company. Our agents are essentially, their agent teams, they're their own businesses. They're our customers, right? And if we're saying we're releasing, you know, the product that's going to tell you whether or not, you know, the homes, you know, of your former clients are now likely to sell or something like that, it's going to be hard to basically be like, oh no, we didn't tell you about some of them because, you know, because we're running an A/B test or something like that. I think it's a little harder there. And then, yeah, I mean, my good friend Ronnie Kohavi is spending a lot of his time trying to actually convince other sorts of companies that they should be figuring out how to do A/B tests. Companies have done causal inference sorts of tests for a long time, but it's, you know, a lot of times it'll be like, yeah, we release things at different times in different markets, and these markets we know with respect to our product are very similar. And so we'll introduce it first in this one market and then see. So we get, I mean, if there's any, you know, macro changes in the world that affect our product, we would see that, you know. And so it's essentially a quasi experiment, right? So there's the various kinds of quasi experiments, this being one, another being natural experiments, like something's changed in the world. And so, for instance, for our recommendations, we have a natural experiment, which is that we decided to recommend some things, but for a few reasons, sometimes we don't recommend them. And so that was something that just as well could have been a recommendation, right? And so we essentially have a control there. And then whenever you're doing natural experiments, you still have to get down there and say, is it really kind of random looking, right? Is there a confounding in there? Is there selection bias in what didn't get recommended that actually also would affect the outcome? And that's just hard work, you know, hard data science work. I actually have a little twist on A/B testing, a little data science twist on A/B testing that I actually pulled up a slide for. You want me to show it?
Yeah, please.
This is like, to me, where the A/B testing, which of course there's a lot of data science in A/B testing, and the predictive analytics kind of come together. So let me see if I can figure out how to. This is Spotify's playlists, right? And so Spotify actually uses machine learning algorithms to create these playlists. All right. So let's just say we're the product, we're running product for this particular product, right? And the machine learning team comes and says, we've got a new playlist generation algorithm. It's better than the one we're currently using. You guys should roll it out as soon as possible, right? And so what do we say as product?
Let's test it.
Let's test it, right? I don't believe your little graphs that you show me, right? I want to actually test it, right? So we run an A/B test, right? And so here are the results of the A/B test. Actually, by the way, this was a ABCD test. There were 3 new machine learning algorithms and the incumbent. The incumbent is at 0, and so this is really how much better. And then this was if we picked the best of B, C, D. So we tested B, C, and D, and then this chart just shows what happens if you pick the best. And then this was a huge A/B test, more than 500 million users. And so the idea here was we also just wanted to look to see whether or not having a larger and larger and larger A/B test actually helped you make a better conclusion. And in this case, it turns out that and the confidence band is the pink, and it turns out that yeah, no, we cannot conclude, even with 500 million users, we can't conclude that any of those methods, even if we pick the best one, that it's better.
Right? Yeah, but what were they comparing? Do you know?
There were 4. There was the incumbent method, and then there were 3 new methods, each developed separately. New methods for making playlists.
Oh so yeah, no, but I meant...
so what is the outcome of interest? Right, the outcome is I guess that somehow got chopped off. This was the improvement relative to control. Improvement in what? Essentially, that they had a whole bunch of different targets than they were looking at, but the one that was the best proxy for what they wanted. I mean, they wanted better. They wanted customers who were happier with their product, right? But the best proxy that they had was, do they listen longer?
Mm-hmm.
So that's really what this is showing. This is showing how the increase in how long they listen, right? Again, across 500 million people, then split up into the ABCD test. Okay, why did I put this up there? It turns out this illustrates one of the biggest problems with A/B tests. Right? It turns out that those other algorithms actually are great and do really improve performance.
Mm-hmm.
But they improve performance for some people and they decrease performance for other people. And when you actually try to compute the average effect, they average out, and it turns out that it doesn't do any better. Furthermore, which people it's better for is not like some simple little segment, right? It's like really complicated, right? And this is like, I think, like a new area of data. I mean, this isn't a new area of data science, a new area where data science will be popular. This is a very, people have been talking about this in research for a long time, but I don't see this. Maybe you guys do. I don't see this kind of thing out there in practice at all, really, right? So here is the 3 models that are the competitors. The incumbent is still at 0, right? And then the red line is still, what if you just pick the best of the competitors for everybody, right? So that's just the line we saw before. And the other ones are, what if you learn a machine learning model on top that actually picks the best machine learning model for creating playlists for everybody, right?
There's a model to pick a model.
There's a model to pick the playlist generation algorithm, which is itself based on machine learning, right?
Yeah.
And it turns out you could do a lot better. I mean, a lot better. And furthermore, now you see that the data actually, having larger and larger data, really does make a difference. You have more data, your machine learning is going to work better, right? And so this is essentially the way to do this next action prediction is you run an A/B test, right? Then when you have the A/B test, you have all of the different outcomes and you have them randomly assigned, so there's no selection bias, because I tell you, the machine learning algorithms will pick up on the selection bias and they'll show you what's really better when they're really just taking advantage of some confounding in the data. And so you run the A/B test, then these yellow, blue, and green were assigned randomly to people. And now you have an unconfounded data set that you can now learn. And it's a little complicated to do the evaluation, but you can after the fact, there are statistical techniques after the fact, you can tell what would have been the outcome had you actually put it into practice. And the whole reason you could do that is because it was random. Right.
But isn't it that sort of an idea of a bandit model? Like the bandit,
good question.
You have multiple actions that you can take. In this case, an action is an algorithm. And then you just, you try them all out. And the one that gives the most money, whatever you want to improve in your metric, well, that is what you keep exploiting. And then if you're unsure whether the world changes, you keep running an exploration, and then,
Yeah, excellent question. So this is not bandit modeling. And the difference is bandit modeling, you have to put them into production first, right? So the difference there's a big difference from the product perspective. You have to actually go and build these out into production, and then also build the machine learning in production. So there's a big effort to actually build them in production. And then furthermore, many companies do not want their system changing on the fly, in production, right? And so in cases where you can do those two things, right? The other difference is that the bandit is, it's learning as it goes along, right? And so it's going to be making a lot of suboptimal decisions in the exploration phases, right? This is the case. This is the case. What you would do in the case where you either don't want to invest in building all four of these new methods out into production, even when they might not work at all, or you're not willing to have actually machine learning in production changing the behavior of the system, right? Then what you could do is you take advantage of a huge A/B test, right? And then you can simulate all this stuff on the A/B test data. And because, again, like I was saying before, because it's random, you can actually simulate what would have happened. There's a little statistical math there. It's kind of obvious, it's kind of like, what you can do is you can run along, and when you're evaluating a model, the model says take action A on this person, and the person didn't take action A. So you can't tell what would have happened for that person if they take action A. You just throw it away and you keep going, right? And the fact is it's random. And so the next one is just going to be another random selection, right? And so the next one comes along and you say, what would we have given that action? Yes, we saw the action we would have given. Okay, then we could see what the outcome would have been, right? And because it's random, then you can go through and it's okay to just throw away anything that didn't match what your algorithm said, because there's no selection bias there. And so you're just throwing away random data, and the next one's another random sample. That's the basic idea. Anyway, I thought that's, to me, I like this because a lot of times for a long time, I've been teaching in class, watch out for A/B tests, because this could happen. It could be that you see no effect because the thing is better for some people and worse for other people, and it washes out, right? And it's always felt like, yeah, but would that really happen? Like, and so to see that it actually really happens is, is nice.
Nice. I think, when I was still at Booking, I think we also had something similar, and I remember them also. Yeah, indeed, a way for us to find out if we ran this A/B test, it was inconclusive or negative, to then sort of like find these groups and then have the model to only run on those ones.
Yes. That's essentially the same thing. You can do this. It's essentially the machine learning models either can actually build a model to say which method would be better on which individuals, which was the best method in the graph I just showed. They can estimate the actual outcomes, and then you just pick the one that you estimate to have the highest outcome. They can estimate actually how much better than the control they would be. Those are causal impact models. And then they can just find subsets of the people where the thing performs really well, it performs really poorly, right? Which is, I think, what you're talking about. So you can do, once you have these big A/B test data, and you're not simply thinking about your A/B test as a way to get the average treatment effects to be able to decide You're thinking of it as a resource that you're building, a data asset that you're building. You could do all sorts of other things with that data asset, right?
Yeah. Yeah. Nice. Super interesting. Yuri, you had a question?
Yes, can you give some references to this kind of algorithms that you're describing?
Yes, I can. So if you Google Carlos Fernandez Loria, you should get his name.net. He has a bunch of papers on various aspects of this, including that Spotify paper. So when you Googled that, did you actually find him is the first question, because there's a lot of Carlos Fernandez's. And then there's the one there has with an application to like playlist generation or something like that. There it is.
Cool. Is there any question, comment maybe from someone else in the call? I had maybe, I don't know, I think we have briefly touched on it, but I think a lot of the sort of like the mindset that you try to put on the book, right, is that you should treat data as an asset, right? And you mentioned the example of Capital One, right? They didn't have some data, so then they invested in getting it. But maybe when you already have like something live or something on production, and you maybe have 3-4 ideas on what extra data you think might be useful. How do you, or like, what would you recommend then to try to, well, maybe it's similar to what we were discussing at the beginning, right? From all these 5 new data points that I could invest on getting, how to know which one could probably give me the better results, right? And I guess it's the EROI maybe comes in place again.
Yeah, so there's another thing that's I think not really in the book that maybe I should put in the second edition is so when you're building, I'll talk about predictive analytics, right? Which I see causal analytics as predictive analytics. And the reason is the fundamental thing you're doing in causal analytics is you're predicting both sides of the counterfactual. So you're saying I could take the action or I could not take the action. I could do A, I could do B. I'm predicting what would happen if I took the action. I'm predicting what would happen if I'm not doing the action. And then I look to see what's the difference between those things. That's the causal effect. So it's really causal inference for the kind of thing that we're talking about is another predictive problem. Okay, so for predictive analytics, right, you as I understand the question, it is like you've started, you have some data, you're maybe even building predictive models in that, and then there's a variety of other data you might invest in, right? But how do I actually judge the ROI, expected ROI of those investments, right? Right? So I think you tell yourself a story. Right? I think that's what it comes down to, right? I mean, you tell yourself a story as to why you think those things would be helpful for the thing that you're building. So if I'm building models to predict to estimate the likelihood that the home will sell over the next 12 months, right? I've got a bunch of data, I'm doing that. What other things could affect the likelihood that someone would sell, right? And we build these complicated, so there's another sort of causal model. That's like a theoretical causal model, not a model built from data. It's like, what are all the causal factors that are influencing something, right? And so you draw this out, like you have a graphical model. You have circles and you have lines between them, and you're like, here's this factor would influence that factor. Then you might have that factor influencing. So you can build these out. And then you actually, basically talk to everyone you can about like, can you think of anything else that might be influential in theory, right? So I might say, can you know whether or not the people's kids are all now off to college, right? People's kids are all now off to college. They're not going to need that big house anymore. We know the size of the house, right? If their kids are all off to college, do people know kids are off to college? Well, yes, because as soon as your kid gets like at college age, you start getting materials about colleges. So someone out there knows that your kids are getting ready for college, right? Or kids, someone had a new baby, right? Someone had a new baby. Now, whether you actually can, whether or not it is ethical, legal, or whatever to do these things, I'm not making a comment on, right? But I'm just saying what could influence somebody wanting to get a new home, right? You have a little apartment, you have a baby, you want to get a new home. Do we know whether people have babies? Yes. I had my daughter. You can see some stuff from when she was actually little back there. I had my daughter. It's like, I guess maybe I'm just an idiot, but I was like surprised that like the daughter, she's going to be born any day now, and like all of a sudden you get a bunch of baby formula in the mail. Like, how the formula companies know that my baby's getting ready to be born? Yeah, guess what? They know, right? Right. So the data's out there, and then that would be an instance of, yeah, those things seem really, really predictive. That like if you had a baby a year ago and you haven't moved yet, you're probably really thinking about it, unless you already have a big home, which again, we can tell. We know the size of your home, right? And so that's, I think, what the answer is. You kind of think through and you tell yourself these stories. One other thing. You also want to see very often, I mean, I've been building machine learning models for business applications for probably 30 years now. I still get surprised at how smart the machine learning algorithms are. Right? You give them enough data, it's like when Kasparov got beaten by the AI, and he actually wrote these articles about how smart the AI was and stuff like that. Like, you see this thing working and you're like, wow. And so the thing is they will actually find their own proxy, right? Yeah. And so they, let's just say that you basically want to know whether kids went to college. The machine learning, and we actually see this kind of thing, right? The machine learning can basically be like, well, you're in a really good school district and you moved there 12 years ago, and you have a house that probably only had one kid. And so your kid's either off to work or off to college, right? And so you see, actually, when you look to see why did the machine learning predict that this house was likely to sell, it'll say stuff like that we don't know. I mean, I think this is another issue for product, is that the customers very often want to know why the machine made the decision it did. Like, can never tell you that. We don't know that, right? We could start to give some hints and stuff like that, but who knows what it's thinking, But you could see that it's basically the factors that it used to make this particular decision were the house has been on the market for 12 years, the size of the house, the location it's in, or something like that. And you can then tell yourself a story, which you may be convincing yourself of something that's not true. You can tell yourself a story that like, that's looking like it's thinking that that in this neighborhood, it doesn't know that homeowner's kids went to college. It's like when this kind of thing happens in that neighborhood, you have a big house and now you've been there for 12 years, people start selling their houses, right? And the underlying causal reason is probably because their kids go off. It's a good school district. The property taxes are much, much higher in a good school district. And so they don't need the school anymore and they get out of it.
Yeah.
You don't need the big house anymore either.
Yeah.
I was wondering, in the book, you describe the big theme of we have supervised problems, we have unsupervised problems. Mm-hmm. And when I studied statistics, which isn't that long ago, maybe 10 years ago, I hadn't learned yet about reinforcement learning. So I also still learned, well, there's supervised and there's unsupervised. And then eventually over the last 10 years, I heard about reinforcement learning and I Googled like, well, what is that? Does it fall in one and the other? And then it kind of seems like it's neither. So where would you see that fall?
I see reinforcement learning falling in supervised learning in the same way that this causal prediction does. And so my view is either you have to pull out all this causal prediction, right? And make a new category for it, right? And then reinforcement learning would go into that category, or it's kind of like it's kind of an part of supervised learning. Let me tell you why. I don't put that much stock in the labels. I think the thing about so maybe everybody doesn't know about reinforcement learning. So Cindy mentioned Bandit algorithms before. These days, Bandit algorithms are generally put into the category of reinforcement learning, although they didn't used to be. But the idea is you are observing the taking of actions in the wild and then learning from it, learning some kind of a policy for what actions to take. And so the things that we, the things that we have talked about, sort of already, sort of when they're in the wild, like if we were to do what you had suggested and done the playlist learning in the wild, right? That would be a bandit problem. And so it would probably have fallen into reinforcement learning. But if you do the exact same thing, in vitro, then you would call it supervised learning. And that's one of the reasons why I don't think the label is as informative about the learning. The label is sort of much more about the setting than the learning. It's like one is online and one is offline, really, right? And then the one other thing about reinforcement learning, and the key to what we used to differentiate reinforcement learning, was that there were multiple actions that you take, and you have a hard time assigning credit. So I do this and I do that and I do the other thing, and then something good happens. Which one of those actions, which this is not the case for bandit problems, because bandit problems, you pull the lever and it gives you some money and you're like, I know what action led me to get that money. It's not there's still another question about like how likely is it for this arm to actually give me money next time, but it's not a question of which action I took. And pulling the arm of the bandit last time definitely did not have an influence here. So that's the other part of reinforcement learning. That comes up a lot in robotics when the robot's going around doing stuff. It can come up in sort of soft bots. And then I don't know if I could pull up a compelling example of the full-blown sort of multi-step reinforcement learning in like a non-kind of robot setting, but there must be one. But bandit problems, the bandit problem is ubiquitous. I mean, you want to give people ads, right? You could set it up as a bandit problem and see, start changing the ads you're giving on the fly, sort of optimizing the whatever you're trying to optimize the conversion rate within a short period of time after the ad.
Cool. I'm checking at the time just to be conscious. Maybe one last quick question. You mentioned also you have worked a lot with product managers. What would be your, maybe from a more data scientist point of view, your recommendations for product managers working or maybe getting into more data science heavy products?
Well, one thing, Claudia Perlich actually answered the question for me in her quote about the book. Let me see if I can find it. Can find it quickly here. Claudia is a super top, maybe the best practical data scientist in the world, and she wrote, "I would love it if everyone I had to work with had read this book."
Which book is it?
This one.
Oh.
No, yeah, I mean, seriously, it really helps when the person knows about data science and knows like the fundamentals, and you're not like saying like, you don't have to say, wait a minute, like you don't actually know what machine learning is, do you? Like, you're using the term, but you don't actually know what it is. Like, tell me, what do you think the output of a machine learning program is? So knowing that, and then so that would be, I think, if you're PM and you want to work on that, I think to me, get as much, forget about whether you read my book or not, you probably, especially if you have already, right? Get as much
exposure,
education, whatever we want to call it, so that you're somebody who goes in there and they're like, wow, this person knows what they're talking about, right?
Yeah.
And then I think like the stuff that we've talked about today, you can add value. I'm telling you, the machine learning engineers and the machine learning scientists have a lot of challenges when it comes to actually getting to business impact with machine learning. It's a huge, huge opportunity now, and we're going to see, by the way, we're going to see a lot of press about how, AI doesn't live up to its hype and all that. And the reason is not going to be the AI's fault. It's going to be the people's fault.
Yeah.
And so, that's what I think. I think sort of, make sure you know what you're talking about, and then go and say, I have this angle of adding value, right? I can help to sort of think through what machine learning, you want to do this stupid machine learning thing, I think there's another one that might be better for you,
Yeah, yeah. I do have recommended the book quite a few times, so
Thank you very
I think it works. Awesome. All right. Maybe yeah, just to make sure also we can take like a picture for the ones that they have the book. I think Foster, you also have the book there at hand. Then maybe
yeah.
then we can take a picture with the ones that have it. All right. 3, 2, 1. Cool. All right. Awesome. Thank you. I will send you the email, Foster, with the picture as well. Yeah. Thank you very much, everyone, for joining. Thanks, Foster, for joining.
Thank you guys for inviting me. This was a blast. I really appreciate the interest.
Awesome. All right. Thanks, everyone. Bye-bye.
Thank you.
Hey, everyone. I'm Carlos, and welcome to a new book discussion of productbooklab.com. Every month, we discuss online a book about product management together with the author and other product colleagues. If you want to find the recordings from our previous discussions and also join us and participate on the upcoming ones, go to productbooklab.com. To find out how to support the book club and help us keep it running without any ads, check the links in the description.